All right, welcome to Unit 2, Lesson 5 online. We are going to further develop the idea of work, and I'm also going to be, well, the goal is to be able to pictorially represent energy changes using bar graphs. So we're not actually going to put numbers to this, we're actually going to work back on bar graphs. That'll help us when we get to the more difficult problems. Alright, so here's our review, our equation for energy stretched in a spring. Not too big a deal here. So back to this question here, you can see our spring here, and we stretched it. As we stretched it, alright, the energy increased, but what caused that energy to decrease? And what I argue is that the force this force here causes my energy to increase. And so if we go to our next slide, so the added energy in our spring system as we stretch it out is as a result of an interaction between an external agent and outside the system and the spring. Okay, so the area under the F versus Tx graph represents the energy transfer during an interaction that results in the displacement of the point as a result of that force. So something outside my spring system had to cause that thing to stretch. Okay, when that interaction occurs across a boundary line, we call the process of energy transfer as working, or we'll call it W as far as that goes right here. Okay, when the interaction occurs between objects within the system, then we said that the energy is moved from one mode or to another, and if it's that case, we don't have to identify the force that's causing the work or the working to be done. Okay, so that'll make sense in just a little bit. So it's about energy definitions. This lesson is all about tracking energy changes. And force can cause our energy to change through the process of working. Okay, so work here equals our change in elastic energy. Okay, again, that energy that spring did have, it was due to that process of working. Okay, so now we can use bar graphs to represent our energy transfer. So each bar graph situation you must define the system, its initial conditions, the energy flow, and then the final condition. So we're just going to track energy. That's all these are doing. And then again, it'll help us in the long run. I affectionately refer to these as LOL graphs or laugh out loud graphs. So you'll see these in just a moment. Okay, because you can see the L. Here's the O and the L. And that's again why I'm calling them LOL graphs. Okay, so let's talk about an example of how to use these now with my system. All right, so with our spring system, if I define my system as just the spring, okay, initially before it's stretched, all right, it has essentially zero energy. Okay, at the end, actually I'll skip the middle step. The end, we know when my spring is all stretched, so we take this here, and we stretch it all the way out, we know that it has elastic energy. So again, where does it come from? Well, that's where we get the idea of working. Notice here I have 4 bars. 1, 2, 3, 4. So we have to account for 4 coming in. So again, I have 1, 2, 3, 4 coming in, and identify my agent. So I put working, or you could say just W, done by force due to gravity. When you do these things, you must identify the agent. It's important for our tracking of of this. And our fourth digit of gravity would be the weight, or of what, in the case of our lab, it'd be the weight. 1 by weight, you could also say as well. Also say it like that. So again, this number here at this point is arbitrary. I put 4 in there just because I did. Next worksheet, we're going to quantify this. Again, we're going back a step. We're not going to quantify things this time. We're just going to get used to putting the pictures down. This next example problem, we're going to draw a bar graph for a car skidding to a stop. Okay, so we're going to do initially. Here's our initial. Here's our final. Now again, it depends on how we define our system. We can actually have two separate answers. So I'm going to actually do it 2 ways based on my system. And the first time I'm going to do this, I'm going to draw my system, just my car. Okay, so initially I'll have it as 4 bars of kinetic. Again, it's just an arbitrary number right there. Okay, so now at the end we know that there is no kinetic, it's gone, no gravitational, there's no elastic. So now, did it go into internal? Well, what caused the energy, or where did the energy go? Well, as you can see here, when you slam on the brakes, you get these skid marks here. So it's an interaction between the wheels and the road when you're coming to a stop, because your brakes cause your wheels to lock up. So then where does that energy go? Well, I would say that the energy, since the road is not part of your system, is actually going to leave. It's going to go into our road here. So 1, 2, 3, 4. Again, I have my four bars leaving. I'm going to identify it. So work done by friction from the road. So again, my agent here, my force, which causes that energy change, is identified, and so then it shows a leaving. Now, I'm going to show the alternative way, and a lot of you don't like that we have 2 ways. The other way we could do this is we could define the system as car and road. Now, if we define it as car and the road, we start off as kinetic here like this. And at the end, I would say no work is being done, so nothing leaves my system here, so that just stays steady, and it all goes into our internal like that. And so we show our transfer where we always show energy conserved. So we have 4 blocks here, 4 blocks have to be at the end, and then of course that shows our transfer of energy. So working is the process by which energy is transferred into or out of our system. Energy bars can be used to pictorially represent the energy transfers. When representing the process of energy into or out of a system, through working, always identify the agent. And tomorrow during class, we will work on worksheet 4 in small groups. So that's it. Have a great evening or morning or whatever you'd like to, wherever you're at on this thing.